To review, what do these terms mean? Write definitions in your packet, and I'll put the answers up in a second. How are these glasses of Kool-Aid different from each other? Why is one so light, one so dark, and the other's different shades in the middle? The difference is how much solute particle is dissolved in each glass. The leftmost has very little solute and increases left to right, and the rightmost has a lot of solute. We might use words like dilute and concentrate to describe this phenomenon. Now, dilute means that the amount of solute is very low, so the solution is very, very weak since there's not much solute compared to the amount of the solvent, the liquid. Concentrated means the solute is very densely packed in since there's a lot of it compared to the amount of the liquid solvent. We've used solubility curves recently to visually show how solute dissolves. Now we'll calculate the actual amount to determine a number for concentration. Now again, concentration is a measure that tells how much solute is dissolved as part of a solution. Saying a solution is dilute or concentrated is more general qualitative information, but we can use actual numbers to describe it and give much more specific quantitative information. In this video, we'll take a brief look at a few ways to measure concentration. One of these is by using the solubility curves in Table G, which we've been doing for a couple days. The others are percent composition by either mass or volume, which we've used a few times in the past, and parts per million, which is really similar. Formulas for each of these are on the back page of the reference table. Tomorrow we'll talk about the last way to measure concentration, molarity, which, as the name implies, will measure the solute in moles instead of grams. And this is a really, really important one because it'll come up again throughout the year. As it says here, any question about measuring concentration has to tell you which way you're measuring. Then you can plug numbers into the correct formula in your reference table and do a quick calculation. We've calculated percent composition in a few previous chapters, usually to figure out the makeup of a molecule, but we can use it for either mass or volume, and each uses the same basic formula of part over whole times 100, as you see here, and it's on your reference table. If a question talks about the mass of a sample, then we use mass of the part over mass of the whole times 100. Like we're calculating a percentage of nitrogen in a sample of solid plant fertilizer. And that's pretty much what we've done before. If a question instead uses the wording where they're talking about volume of sample, we use the same formula, we just use volume instead of mass. So now it's the volume of the part divided by the volume of the whole times 100. You might see this like on a bottle of this rubbing alcohol where it says it's a 70% solution of rubbing alcohol. That means 70% of that thing by amount of liquid is rubbing alcohol. The other 30% is the water. For the record, yes, there really should be a little green owl on these slides since these are all reference table things, but I forgot to put on, and I honestly don't want to make the effort to go back and add them now. It would require me to use two different computers and go back and forth, and that's really just more than I feel like doing at 10 p.m., so pretend poor little Otis is on this slide. Pause the video and do these example calculations using the part over whole times 100 formula in your reference table. Then unpause and I'll write the answers. In this question, it tells you what the total volume is. You don't have to actually add these things together. If the question uses the phrase, the total volume is this already, just write that number as your total. All right, two more of these. This one says percent by mass of NaCl, so we're going to find NaCl as our part over the whole in the solution. So again, it's part over whole, and these are mass questions. So it's the mass of the part over the mass of the whole times 100 as always. It tells us we have 10 grams of NaCl dissolved. That's our part, so we put 10 grams on top of the fraction. For the whole, it says the 10 grams of salt are dissolved in 15 grams of water. So we have to add those two quantities together. So the 10 plus 15 grams we add together will give us a total of 25 grams. That's our whole at the bottom. So 10 grams divided by 25 grams. Don't forget to multiply by 100. And when we do 10 over 25 times 100, that comes out to 40%. So 40% of this salt water solution is the actual salt part and not the water. Next question is a volume question. So now it's volume of the part over volume of the whole, but it's still the same formula. Reference table says it as the mass version, but you can do the exact same thing for volume. That should say 100. And it says now we're adding 75 milliliters of ethanol, a type of alcohol, into 125,000 milliliters of water. So that's not the total. We have to actually add these things together. So our total will now just be 125,075. We'll put that at the bottom. So we have our 75 milliliters of ethanol as our part. As the whole on the bottom, it's the 125,000 plus 75. So it's 125,075 milliliters. And we times that whole thing by 100. And when we get our answer, it's a really small decimal. This is going to be 0.0599% by what I have written down here. So that's a really tiny percentage. That's really not going to be too helpful for us. It would be really much easier if we had a better way to measure small little amounts like this, because that's really not a particularly useful thing to look at. So we'll see how we can do that on the next slide. Now the glamorous life of science. If we were someone trying to answer this question about how much pee is in the average public swimming pool, we'd hopefully be able to assume that any urine is in fairly small amounts. That would help us sleep better at night, right? If this was true, the percentage would be a very, very small number. So to measure that, we need to adjust our formula a bit and figure out how we can measure these very small amounts. If you ever watched Shark Week and heard that a shark can detect a drop of blood from a mile away or whatever that ridiculous stat is, this is close to how you measure it. Cutting a pie into 10 pieces lets you measure it in tenths, or a part per 10. If we cut into 100, it's a part per 100, which is basically what percent is. But if we cut the pie into 1,000,000 pieces, it would let us measure things as a part per million. So per 1,000,000 pieces, how many are we talking about? If you cut something and divide it into 1,000,000 pieces, how many are you actually looking at? And that's going to let us measure very, very small quantities of solute. This formula for parts per million is just like the percent composition formula. It's basically the same thing, except you multiply it by 1,000,000 instead of 100. The parts per million is part over the whole. This formula here says mass of the solute, that's the smaller part, over the mass of the solution, which is the whole. So it's still just like part of the whole. It's just worded a little bit differently on the reference table. Now, it lets us measure very, very small amounts of things that are just basically too tiny to be given a meaningful measurement when using percent composition. When we just divide our whole into 100 parts, the thing we're looking for is going to be much smaller than 1/100th. So we just need a better way to do it. And as you're doing this, just again, be careful to multiply by the correct number. If you multiply it by 100 by mistake or by 1,000, you miss a 0 or 2 somewhere, you're going to mess up your entire answer. Just make sure you're doing the same kind of step as before, but multiplying by a full 1,000,000 when you do your final math. In this question at the bottom, it says we're going to take 0.0043 grams of salt and dissolve it into 100 grams of water. So we can see it's a really, really small amount we're adding in. So the thing we're looking for, our part is the 0.0043 grams. I'm not sure why my pen isn't letting me write particularly well here, but that's my part. And for the whole on the bottom, we have to add these two numbers together. So it's going to be 100 plus 0.0043. That gives me a total on the bottom of 100.0043. So still a pretty small addition we add in. And now we multiply the whole thing by 1,000,000. So 1, 2, 3, another 3 zeros. Multiply it out. And when we do this, we should get an answer of 42. And our unit is ppm, parts per million. That means if we divided these 100.0043 milliliters of, grams of salt water into 1,000,000 little pieces, 42 of those 1,000,000 pieces would be just the salt. So it's a really small amount, and it helps us do this instead of using the percent composition. By dividing to a million pieces, we can see a much more clear number without getting one of those teeny tiny little percentages that are not really helpful for us to look at. Just be careful when you're doing these types of questions. Like we saw before, if a question says you add this solute to this solvent, just add those two numbers together to get your whole. But if a question says this amount of solute was dissolved into a total volume of solution, and then they give you a number, like with the one where it said, I think 300 grams of water, just use that as your number. So you just got to be really careful of how the wording goes. But let's do these two last examples, and then we're done. If 0.025 grams of lead nitrate are dissolved in 100 grams of water, what's the concentration of the resulting solution in parts per million? Again, notice the question has to tell you this is the way we're measuring it. If it said parts per million, use parts per million. If it says percent composition, use percent composition. But for this, we have our part, which is 0.025 grams. And then for our whole, it says we're adding this mass, 0.025 grams, into an additional 100 grams of water. So our whole, our total mass, is going to be that 100.025 grams. So we do 0.025 grams divided by 100.025 grams. And again, remember to multiply the whole thing by 1 million. That's a comma there, 1 million. And when multiplied out, it should say 249.9. I'm going to round it up to 250. That means if we mix these things together, the 0.025 grams of lead nitrate with 100 grams of water, and then we took the whole solution and cut it up somehow into 1 million equal little pieces, 250 of those million pieces would be this stuff, the solute, the lead nitrate. So 250 parts per million, or ppm, is our answer there. For the second and final question, very similar. What's the concentration in parts per million? Again, it tells us what formula we have to use, parts per million. If 0.02 grams of sodium phosphate are dissolved in now 1,000 grams of water. So again, this is our part, 0.02 grams. And for our whole, we just add these numbers together. We're taking 1,000 grams of water and mixing 0.02 grams of sodium phosphate into that. So our whole, our total is going to be 1,000.02. And again, don't forget to multiply it by a million. I don't feel like writing all the zeros, so let's just write 1m. And that will give us an answer of 19.9. And again, I'm just going to round that number off to 20. So once again, if we took 1,000 grams of water and 0.02 grams of this sodium phosphate and add that together to make some solution, and then we were somehow able to divide that into 1 million equal little pieces, of those million pieces, only 20 of them would be made up of the actual solute, the sodium phosphate. The rest would be the water component. Do what it says, and tomorrow we'll do some more math.